This is for our class. Are we taking notes? Not right now. I want you to watch. All right? This was part of the homework. This is going to be on the EOC. So what we're going to do is, do you see this rectangle? See that blue rectangle? I'm going to spin it about this axis of rotation. I'm going to spin it. And the question is, if you take this rectangle and you spin it around, what are you going to get? What figure? What three-dimensional figure? It's going to...
Oh, well, it's like that thing. No. That thing. No, that's thing.
You're going to spin it, so there's going to be something circular to it.
No.
Not a sphere because it's flat on top and flat on the bottom.
It's what is it called? Cylinder.
What's a real-world example of a cylinder?
A
A can. Let's watch. You ready? Here it goes. Watch it spin. What are you seeing? It's a very short one, isn't it? No, look. Look at the height. There's a height to that can. Maybe this looks more like a disc with no hole. Yeah, it's like a... Yes. All right. Are you with me? All right. So now, what happens... Shh, reset. What happens if I were to now not let it touch the axis of rotation? Now when I spin it, what are we going to have? Well, okay, it's going to be a very flat-looking donut. It's going to be our cylinder with a what?
Oh, it's going to be one of those baked things.
But it's going to be flat.
Yes. Or pineapple.
Okay.
Yes, a slice of a pineapple.
Slice of a pineapple if they've taken out that center. Do you know what a washer is? Not like that they use with nuts and bolts? Yeah.
What? Yeah.
All right.
Oh, yeah. Could be.
All right. So now let's spin a region. All right. So you ready? Do you see that blue? What is that going to look like if I were to spin it about that horizontal axis? Well, it's not going to be quite a cylinder, but you're going to be given two-dimensional objects. It's circular on the bottom. Yeah, it looks more like a cup. Exactly. And it's flat here. There's a small circle, then there's a bigger circle, and it kind of curves up. That's more straight sides. I don't know what that shape's called, but that's a square root function that's spun. No. All right. So now what I want to do is I want to move the axis away. What do you think you're going to have? It's going to be bigger. It's going to look the same, except there's going to be a hole in it. Revolve. All right, hold on. There you go. Isn't this kind of cool program? Are these in the notes? No, this I decided to use because I think it helps you to see it. You see it? Now, this could be a lamp because now we have a hole for the cord to go through. You know what I mean? Put a hole for a... But it's the same figure, but now if you tried to fill that and use it as a cup, would it be very useful? No. Right. Yeah, a lampshade. That's a really good. Very thick lampshade. Very thick. All right. So does that help you see these volumes of revolution? Okay, that's one of the things they expect you to be able to do.
Wait, so what's a volume?
That's the figure made after you revolve.
Oh.
Rotate that piece. All right. So today we got lots and lots and lots and lots and lots of vocabulary. So it's a major vocabulary day. So let's talk about this EOC because this is great because EOC is coming. The window is April 29th through May 4th. So it is coming quickly. April 17th is when I think I will give you the last test, or maybe sooner. We'll see.
May 11 to 11.3 for 1.
11, today is section 11 to 11.3.
We don't have any EOC.
Okay, on A47, which was over the weekend, there was no number 1. So today, on 11 to 11.3, I will update that. Make this notation. On 11 to 11.3, you do have 2 EOCs, 1 and 2. Now, it says that, it says PA and AM, bless you, are tangent to circle O. So if this is tangent to the circle and this is tangent to that circle, from a point outside the circle, what do we know about those two segments? They are congruent. All right, that was one of the theorems we had back in Unit 3. That was a long, long time ago. Yes. So if PA, that should be equals 6x minus 5, and MA equals 4x plus 17, what's the value of x? Correct. Now let's look at this next one. What do you know about a tangent and a radius? What do you know about that intersection? 90 degrees. When you see that radius and you see that tangent, you should see 90 degrees, all right? Think 90. It says PCA. PCA is 80 degrees. That's 80 degrees. And CP is 6. How do you, now they've asked for AM, but that's kind of silly, isn't it? Because what is AM equal to?
What you got from the form?
PA. So how do we find, to find AM, what do we need to find? PA. What do you think you're going to use to do that? Yes, exactly. You're going to use trig. And this is great. This is very good because your Unit 6 project is on trig.
Yep.
All right, so our essential question is, how do you find the volume of three-dimensional figures, and what is the ratio of similitude, and how is it used? This is the last part of the curriculum for geometry that we have to do this year. But before we can go into the volume, we first need our vocabulary. So polyhedron is a solid formed by polygons. 11.2, 11.3, that enclose a single region of space. So you take a bunch of polygons, put them together, and make an enclosed figure, then you've got a polyhedron. The faces of a polyhedron are the polygonal surfaces. And I'll put flat.
Is whoever sits your first period?
They have a Starbucks.
Oh, really? Good bench.
All right, and we're going to name some of these faces. So I will name a face first. So if we look at this, A, D, H, E names the left side. So we've got A, D, H, E. Notice I went in order. All right, that's the right side. Who can name the left side? Mackenzie, you want to name the left side?
Like the first one.
Mm-hmm. Okay, so you did a nice job going in order of the vertices. B, C, G, F. You could have started down, but then you would have had to go around. You could have started at any one of those 4 points. All right, so that is the left side. Let's see. Alexandra, can you name the back? Mm-hmm. Good, and you did a nice counterclockwise, that's clockwise, motion of those. All right, who can name the front? Okay, Hale? All right, C, G, H, D is the front, so we've got left, right, top, bottom, no, front, back. How about the top? Ethan? A, B, C, D. Samantha, bottom? E, F, G, H. Edges of a polyhedron are the segments where two faces intersect. Segments, so I should see segment notation, are segments where two faces intersect. So one edge is AD. AD is an edge. Notice my segment notation. That's where the top and the left intersect. Give me another edge. Lizzie? BC is its corresponding part on the other side. All right, give me another edge, Elber. AB. And give me another edge, Stephanie. Maybe I should mark these as we do them.
Wait, can you explain that?
Edge. Okay, so BC is where the top and this side meet. That's an edge. AB is where the back and the top meet.
So like this.
Yeah, it's like a corner of the box. Not corner. It's an edge of the box. CD. CD is another one, and that's where the top and the front meet.
Could you do like AE?
AE.
Yeah.
AE is another one. That is where the back and the side meet.
So basically it's just like all where the lines are.
Right. So Brian, name another one.
F.
FG. Where's FG? FG's down here. That's an edge. All right. Caitlin. DH. EH. So we've got EH. Here is EH. Yep. Another one, Madison King. HG. HG. Yep.
Yeah.
HG. We've got EF. Yep. There's more.
Yeah.
Hold on. Which one?
Yeah.
BF. And I heard something with H. DH. Okay, so BF, DH, and CG. Did I mark them all? All right, lots of edges, aren't there? Okay. So now let's go to vertices. Vertices of a polyhedron are the points of intersection of three or more edges. Now you can read in your book, Euler is a famous mathematician. They came up with a relationship between faces, edges, and vertices, which is nice. But I don't see where that's something worthy of knowing 20 years from now. Now maybe finding the volume of one of these, maybe. All right, an example of a vertex is A. You see, at A, we've got this edge and that edge all coming together. So those are three edges that intersect at A. What's another one? B. And at B, you've got A, B, C, B, and FB coming together. I heard C. C's another one. We've got 1, 2, 3 coming together. What's another one? D. D, we've got these two tops and that side coming together. I think there's more. E, there's E. H and F. H and F and G. Those are your vertices. Any questions? Three edges come together. Yeah. Uh-huh. Does that explain why? All right. So now we're going to, all right, so we're going to come back here and we're going to fine tune this, all right? A lot of we're going to be focusing on prisms. And most of the time the bases are the non-rectangular sides. Now, if everything's a rectangle, then the bases are rectangular. Non-rectangle sides, for the most part, all right? For the most part. Now, if everything's a rectangle, then it's a rectangular prism, and a base would be a rectangle. So of our faces, we have what we call bases. The base is the non-rectangular sides. A, B, C, D is a trapezoid, therefore it is a base. E, F, G, H is also a base because it's a trapezoid, which makes all of these over here non-bases. And for these, we usually use the word face. And if you want more specifics, we'll call those lateral faces. Lateral usually means side, not the top and the bottom. Now, I just want you to be aware that I can rotate this figure, and I could have it this way. These are still the bases because those are the trapezoids. So the bases, it doesn't have to be sitting on the base. You with me? Because most likely, if I'm going to ask you about vocabulary, I will have it so it's rotated to make sure you understand what's going on. So I want you to be aware that there's two types of faces, and there's two types of edges. Lateral face and base. Faces. And base. Now, we also have base edges, and we have lateral edges. All right, remember, two plane figures, two flat surfaces intersect to give you an edge. So if it involves a base, like AB is the intersection of the top base with the back side, that would be considered a base edge. So I think what I'll do is base edges I'm going to highlight in green because I'm not sure, I think they're all over the place. So AB is a base edge. Can someone give me another base edge? AD is a base edge. DC is a base edge, and BC is a base edge. There are four more.
Oh, EH.
EH is a base edge.
EF.
EF is a base edge. FG is a base edge. HG is a... It is a base edge because it's the bottom and the top. All right. So lateral edges are literally formed by two of the sides intersecting, like the right side and the front intersect at CG. That is a lateral edge. It doesn't involve the base at all. What's another lateral edge? BF, that's the back and the side. Another one? AE, BC involves the base. So BC is not. But AE is the back and the side, so AE is one. DH happens to be the front and that left side, so it's a lateral edge.
Lateral edge is two faces.
It's where two faces intersect. Base edge is where a lateral face and a base intersect. All right, so then we get to vertices. Vertices are vertices. So who can name, and that would be faces or lateral faces? What's one of the lateral faces? And actually, when I go to do this, YX, YS is a lateral edge.
A face would have to have four.
A face would be a surface. WEGH. That is a lateral face. It's that back part. Can someone name another one? WQAH. That would be this one there. You could have done this one or that one.
The top.
Oh, well, the top is not a lateral face. It's a what?
Face.
It's a base. So how do we do the base? Okay, what's the other one? There's only one more. GFDSA. Those are the, and I usually identify my bases. What shape is the base? Huh. 6 sides? Hexagon. I usually identify my bases and then I can see my faces a little bit easier. We have named one lateral edge. What's another lateral edge?
TD.
TD. And I heard what else? WH, EG, RF, QA. Now, what is a base edge? AS would be a base edge because it's on the base. SD, DF, FG, GH, etc. Yeah, you have some vocabulary. All right. So now, regular polyhedron or polyhedron whose faces are the same congruent polygons. So like a cube, where every side is a square, would be a regular polyhedron. But we're going to only focus on two, prisms and pyramids. That didn't work. Prisms and pyramids. So a prism is a special type of polyhedron with two parallel congruent faces. Two parallel congruent, and I think instead of faces I would prefer to say bases, called the, oh, there it is, two congruent faces called the bases, and whose other faces are parallelograms or rectangles. My goodness. Right. So they're named for their bases. So let's come over here. What's the different polygon? What are the bases in this figure? Triangles. So this is called a triangular prism. What are these bases? No. Trapezoids. So this is a trapezoidal prism. Now, what's special about everything over here? It's all what? Not necessarily. They're all rectangles. So this is going to be a rectangular prism. So even if I were to rotate this, this is still a trapezoidal prism. If I were to rotate this, this is still a triangular prism. So it's important that you know this vocab. All right, what do you think this is called? What is this one called?
Hexagonal?
This one. Okay, this one is a hexagon. This is hard to see.
It is hard to
It's the colors. That's a hexagonal prism. What is this one? Pentagonal, because the bases are a what? Right, a pentagon. So, are those words from Unit 7 important? Yeah. Those words are important from Unit 7. All right, altitude of a prism. This is, I left out some words. Altitude of a prism is any perpendicular segment from one base to the plane of the other base. The height of a prism is the length of the altitude. What's the relationship between any height and base? Perpendicular. That is true on 2D figures and on 3D figures. So altitude is the perpendicular segment from one base to the plane of the other, and then the height is the length of that altitude. Now, we have right prisms and we have oblique prisms. Right prisms, the lateral faces are perpendicular to the bases. That means every one of these rectangular sides is perpendicular. This is a right pentagonal prism. In an oblique prism, lateral faces are not perpendicular to the bases. There's actually a building in Italy that would be called an oblique prism. Do you know what that one's called? It's famous. Leaning Tower of Pisa. So look at this. You see how they kind of are slanted? This is the height right there. Yeah, I'll move it up. This is the height right there. Notice it's from the top base, but it's perpendicular to the plane of the bottom base. That's why we had to say plane. Now, someone first period said that the oblique prism volume would be different than the right prism volume. And if they have the same base and the same height, that's not going to be true. Okay, this is a ream of paper, okay? And right now it's supposed to be as much of a right prism as possible. Do you agree? Now, if I were to take this paper and I were to just kind of push this, what have I now formed? There is an oblique, right, or rectangular prism. Did I remove any paper? So what can you tell me about the volume of this oblique rectangular prism and its original? All right. Is the shape of the base the same? So that base area didn't change. Is the distance from the top piece of paper to the bottom the same? The perpendicular distance. That's why this volume is the same as the other volume, because it's about base area times the height, and neither one of those changed, even though it was crooked. But that's a foreshadowing of tomorrow. All right. So now let's see so do you see the oblique ones? Everybody see the oblique ones? All right. So a pyramid is a special polyhedron with only one what? How many did prisms have? two, whose lateral faces are no longer rectangles, they are what? Triangles. Where's a real-life example of a pyramid? In Egypt. And what are they used for? Why were they built? We know. And they're big. They're enormous. And think about, they were built but when man didn't have machines to build. It was all human labor. All right, what do you think the left one is called? Again, they're classified according to their bases. Every one of those faces are triangles, so this is a triangular prism. Now on this next one, notice all those little marks. What do you think this one's called? It's going to be square. Why? If otherwise, I would have said rectangular. If it had not had these marks right here, you see those? Right there? If it hadn't had those, I would have said rectangular. Notice the height goes from the point perpendicular to the base, correct. Now, this thing right here is called the slant height. And now I need a different color pen because I'm running H-E-I-G-H-T. That's the slant height. Why is that called the slant height? It's this. This is the height of the pyramid. This is the slant height because it's the height of one of the faces. A slant height, actually they use L. Yeah. All right. Yes. Oh, I'm so sorry. Thank you. And you're the only one that caught that. I bet. How many people wrote prism?
How many people wrote that? Oh, there you go.
Brian, just burst my bubble first day back. All right. What is this first one called? Pentagonal.
How do you see that?
Pentagonal pyramid. What's number 2? Hexagonal. Is it blurry?
That colorful one's not funky.
I got those off the internet. They might be blurry.
I know.
What about this number 3? Yeah, we don't have any information that that's a square. So that's a rectangular. Okay, I did not spell that right. How about, right? You'd have to know that those 4 sides are equal, like on that other one. Square pyramid. I think most of the Egyptian pyramids square pyramids. All right, sphere is the set of all points in space. So important, in space, that are equidistant. What does that mean?
Equally distant.
Equally distant. That are equidistant from a given point. Now, I received actually a practice EOC from the FSA, who's, I guess, the writers of the test, over the break. And this was a what's wrong with this kid's thinking. All right. And it had to do with a circle. Let's define a circle again. Circle is the set of all points. Is it all the same so far? In a plane that are equidistant from a given point. So this definition is exactly the same as a sphere except for what? In a plane. Okay, and on the practice EOC, a kid defined a circle and they said is the set of all points that are equidistant from a given point. So he left out space, but the fact that he did not restrict it to a plane meant it was a sphere. Radius of a sphere, similar to a circle, it starts from the center and stops on the sphere. Now, great circle, operative word here, great, is the intersection of a plane and a sphere, and the plane must contain the center. In other words, this is the largest cross-section of a circle you can get. If I were to draw a circle up here, do you agree that that circle is going to be smaller than that circle? If I were to cut the circle or sphere up here, if I were to cut it here, do you agree that this circle is still smaller than the great circle? Now, there's an infinite number of great circles because you could take your knife any angle you want as long as it goes through the center and you'll have a great circle. On a sphere, like on the Earth, the shortest distance between 2 points is found along a great circle. So sometimes you may wonder why the airplane you are flying in is going in this direction when it seems to think maybe on ground it would be shorter this way. It may be that they're following the great circle. Or then it, again, may be that it's easier to go to their main hub and get people out of there from there. But great circles have a lot to do with the airline industry. If it's a non-stop, what's the shortest distance between 2 points? Great circle. All right, what else do we have? Hemisphere, that was a really good picture too, but the colors aren't good, is half a sphere. Did you know that? And its base is circular. How many people knew that? Okay, so I didn't tell you anything new today. Cylinders are prisms. See, cylinders are prisms. Notice I put it in quotation marks because a prism has a polygonal base. But I think of cylinders as prisms with circular bases. That way I take it from 4 formulas down to 2 as far as volume. And I think of cones as pyramids with circular bases. So there's an example of cones. There's an example of a cylinder. Real world example would be a can, a soup can, a Coke can. This is, what would we label this? Yeah, but what kind? It's special. It is an oblique cone because it's tilted. But this is a right cone. Think of the ice cream cone that you would put ice cream in. Why don't they make things, let's say these cylinders that would be oblique? Why don't you see very many of those?
Weird.
Think about stacking the soup cans if they were oblique.
You wouldn't be able to.
No, they wouldn't work very well. All right, then in CC18, activity 1, and you saw this on Sketchpad. If I were to spin this rectangle around line L, what would you get? You would get a tall cylinder, wouldn't you? And what kind of radius would it be? Radius is 2. What if you were to spin it on this line? Is it still a cylinder? It would be a short cylinder, but now what is its radius? Radius would be 8 feet. I'm going to collect A47 tomorrow because a lot of the vocabulary you needed was in this section.
Should we redo it, Deborah?
You can look at it because when it says list the faces,
Yeah.
then you need to list them, not just tell me there were 5. There is no EOC. Okay, again, there is no EOC on 847, but on 848, it doesn't say there's an EOC, but there were 2, weren't there? And I will send out a Remind 101, and I'll make sure that I change it in the spreadsheet. Send out a what? A link to the EOC. Just go on Portal and go on to, yeah, it's on there now. And I will make sure, and I know that's up there, and I will change the spreadsheet on Portal to reflect it also. Have a good day. Welcome back.